Hey folks, and welcome to another edition of the Tutor's Guide. We're going to be talking some more about exponentials and logs. This is the third video in this series. In the first, we talked about how to evaluate exponential and log stuff algebraically, which I'm about to do a little reminder of. And in the second, we talked about graphing, which maybe I need to do some additional examples of that for illustration purposes. But I definitely want to come back to how we deal with logs and exponentials here. So I've got 4 questions on the board as practice here. The first, we have x to the 5th equals 125. That is not an exponential function. That is a a polynomial. That's the word I was looking for. A polynomial function. So yeah, I hit this wait, what? Poly what? Okay. So polynomial functions, we don't solve using logarithms because the inverse to a polynomial is a root. So if we wanted to solve x to the 5th equals 125, we're just going to say, well, we need to undo the 5th power, so let's do the 5th root. And of course, if we do it to one side, we have to do it to the other. So x is equal to the 5th root of 125, and you can go to a calculator and find out what that number is equal to if you're interested. In the second example, 5 to the x, now this is exponential because the variable is up top. This particular example, we're able to write the right side of the equation as a power of 5, and so now we recognize that when the bases match, the powers must also match, and this is just x equals 3. But we can no longer do that with this third example because 225 is not conveniently magically a power of 5. There are only a very small number of values that will meet that description. So instead, we're going to, and why did I write 5 to the 3rd? We are going to have to undo the 5 to the. And the way that we are going to undo that is by applying the inverse to an exponential, which is a logarithm. So we're going to do logarithm on both sides. And when we do that, we have to remember that we need to use the specific logarithm that is for this base. The base of our exponent is 5 to the x, so we're going to need to use log base 5. And when we do that, the left side, log base 5 of 5 to the x, the reason we did this is because the log and the exponential cancel, and we're just left with x. X equals whatever this is, and we can go to our calculator and we can ask the calculator, hey calculator, what is this? And we will find that this is about 3.36, oh, it rounds up. No, it doesn't, 3.365. Okay, so that's all good and fine, but then what happens if we end up going in the other direction? What if we have a logarithm? So in order to deal with a logarithm being solved, we need to say, well, the inverse to a logarithm is an exponential. So we're going to, instead of doing a logarithm on both sides, we're going to do an exponential. We're going to exponentiate both sides. And since the base of our log is 5, it means the base of our exponent should be 5. So we're going to do 5 to the on both sides. And if we do 5 to the on both sides, the 5 and the log 5 are going to cancel here. And this is going to become x again. And once again, 5 to the 2.25 is something we can put into our calculator if it's not something we can do ourselves. And in this case, it's going to be about 37.384. And you can argue maybe I should be putting approximately symbols here since it's rounded. While we're at it, just for reference, 125 to the 1/5 power, for those keeping score at home, this is equal to 2.627. Okay, so that's a reminder of how we do this stuff. Now, we have to branch out and talk about some other junk. The first of which is we need to talk about the number e. Wait, that's a letter. Yeah, e. E is a very special number. If you remember, when you first started learning about circles, probably in like 4th or 5th grade, and then later you had this reinforced geometry class, and you learned about circumference and diameter. You said, oh, circumference is the diameter times this weird number that looks like 2 sticks with a wavy tabletop on it. And of course we know that as pi. What is pi? Pi is, I don't know, it's some weird number. It's 3.14, right? Except it's not 3.14, it's 3.1415, blah, 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 and goes on and on forever and never repeats. So we have this weird irrational number pi, and you go, why pi? And I don't have a good answer for that. It just is. We have another number here in E, the letter E, just lowercase the letter E, that just is. And E is equal to 2.7182818, and it looks like it's repeating, but in fact after this point it stops doing predictable things. So I know that many digits very easily, but after that I have no idea what E does. And this is a number that shows up in a ton of exponential related stuff. Now, if you want to be more exact, E is the limit as x goes to infinity of 1 plus 1 over x to the x. So we just say we're going to take this expression, we're going to make x bigger and bigger and basically make it go to infinity, and it's going to get closer and closer to this weird number E. Now you don't need to know that. You absolutely do not need to know that, and there are other ways of writing E, by the way. But what you do need to know is it's a number, and that's really about it. Specifically, it's a number between 2 and 3. A little closer to 3 than 2, but between 2 and 3. And beyond that, you really don't need to know much. You just go, well, pi is some weird number I deal with. E is just some other weird number we deal with. Because of the way it's defined, we are going to see it show up later in compound interest, which is a subject that I'm going to save for its own video. But we are going to talk about E here because it gets used extensively in our chapter. So it's worth noting that if I say e to the x equals 50, well, we can solve that. We just have to do log base e on both sides. And that is exactly what we will do, is we will say log base e. The thing is, rather than getting complicated about this, yes, the left side is equal to x, but what I want to point out is that log base e has a special name. Let me switch to the text tool here for a second. Log base e is called the natural logarithm. And we abbreviate that ln. And you might go, why is it ln, not nl? Because a French person named it. So it's logarithm naturel in French. But there is a button on your calculator right on the front that just says ln. So if we want to answer this question over here, it's just ln 50. So we can literally just hit the ln button with typing in 50, and we will get that x is about 3.912-ish. And that's all you need to know, is just log base e is called ln. Now, this is one special logarithm. You might have noticed there is a button on the front of most calculators that just says log. And what's the deal with that? Well, what if I asked you to solve for me 10 to the x is equal to 98765. Now, this is very close to 100,000. 100,000 is a 1 with 5 zeros, which means it's very close to 10 to the 5th power. So we know the answer is going to be really close to 5. Because the exponent, if you put a 5 here, you get 100,000. We're very close. But that's not quite right. So of course, we're going to do a log on both sides. We're going to do log base 10 of 10 to the x is equal to log base 10 of that number. And once again, I'm going to point out that log base 10 is called the common log. This is the LOG button on your calculator. So when you see that LOG on the front, that's what we're going to use right here. So the left side of log base 10 of 10 to the x, this reduces to just x. And over here, we're just going to write log with nothing under here, because this is now common log of 98765. So we'll go to our calculator and we'll ask, what is common log of 98765? And predictably enough, it is in fact super close to 5. It is 4.995. So we are 5/1000ths away. So E is the most important takeaway here, is recognizing that log base E is ln. If you don't write any number under your log, though, that is considered to be base 10. There really isn't much beyond that to say about common log or natural log. You need to know what they are. You absolutely will need to know this information right here. But you don't need to make a big deal out of it. We don't need to go, oh, let's graph these. Oh, let's do a bazillion practice problems. Oh, let's do this. Oh, let's do that. We do need to remember, of course, that if we are solving the other way, we need to know what's going on. So if I say ln of x is equal to 5, we need to think of this as log base e. So in order to undo a log base e of x, we're going to need to exponentiate both sides by doing e to the on both sides. And now if we do e to the on both sides, the power and the logarithm cancel. We get x equals, and we get whatever e to the 5th is. And you can figure that out on your calculator. There is an e on your calculator. If you're talking about TI-83 specifically, just plain old e is over the division button, but over the ln button, there is an e to the x. So I'm going to hit e to the x, and then I'm just going to type 5. And we get 148.413. Similarly, if I said logx is equal to 7.2, we're going to remember that this, if it doesn't have a base specified, is log base 10. And we are going to need to exponentiate both sides. So we are going to do 10 to the on both sides. And so 10 to the log base 10 of x equals 10 to the 7.2, cancel. These reduce. We get x equals whatever the heck that is. 10 to the 7.2 is, according to my calculator, 1584891, comma, comma. So about 15 million-ish. I guess closer to 16 million. Now, the reason why log base 10 gets its own thing is because 10 is the most important number in our numbering system. We literally use a numbering system called base 10, right? Computers don't do that. Computers use base 2, aka binary. They only have ones and zeros. They don't have all these other digits. We go up to 9. Once we go past 9, then we start over with a new column, a new digit. That is entirely based around the number 10. And of course, the number 10 came from the fact that we have 10 digits on our hands. So this is the gist of ln and log. And now we need to move into something else. In fact, I want to start a new slide so I have room. So we are going to talk now about logarithm properties. Now, I'm assuming that you know your exponent properties. So let's just remind ourselves real fast here. Exponent properties, if we have like x to the a times x to the b, for example, if this was x squared times x cubed, we would add those powers together. If we have x to the a to the b, this is equal to x to the a times b. If we have x to the a divided by x to the b, then we subtract. And there are analogs to these in logarithms. I'm not going to get into the specifics of how they match up, but there are variations on this that are significant here. So log properties. The first thing is, if you have some particular base of two numbers that are multiplied on the inside, it turns out, oh, I shouldn't use A and B because I have log base B, so X times Y. What you can do is you can write it as two different logarithms that are added together. And this is vaguely kind of sort of similar to this first one here. Similarly, if you have a division on the inside, you can do the same thing, except that you will be subtracting. And finally, if you have a power on the inside, so if I say x to the, I'll say x to the p, and this is all on the inside of the logarithm. It's not log base b of x, parentheses, to the p. If it's x to the p on the inside, we can say that this is the same as log base b of x times p. And I'm not going to justify those to you. They can be proven, but they are true statements, and we're going to play with them a little bit. So there are two ways that teachers will throw this at you. The most common way is they'll tell you to, quote, expand and contract. And these are kind of dumb questions most of the time. But if I were to say, write the following expression as a single logarithm, then you're going to go, oh, okay, well, according to the second property, this is equal to log of a cubed b to the 7th square root of c minus log of d to the 5th. And then according to the first property, we can break it apart. We can say this is log of a cubed plus log of, log of b to the 7th plus log of the square root of c, and then we'll bring the rest of it down, log of d to the 5th. And then you can use the third property. I'm going to number these just because we're going to keep referring to them. So property number 3, and we can bring our coefficients out front here and say 3 log of a plus 7 log of b plus, okay, let's think about this. Square root of c is the same thing as c to the 1/2, right? So 1/2 log of c minus 5 log of d. And this is, quote, expand the logarithm. When you see the word expand, this is what the teacher's expecting you to do. Sometimes they will say instead to write using a single logarithm. And now we're going to do the exact opposite. So we're going to take something like 5 log of, let's use some different letters, f, I guess f isn't really a good part of the alphabet, m, plus 2/3 log n minus 6 log p. All right, so first of all, let's use property number 3, but we're going to go in this direction. So we're going to say that the 5 goes up top as a power, log of m to the 5th, plus log of n to the 2/3 minus log of p to the 6th. And you'll notice I'm writing all of these as common log just because I'm lazy and don't want to write a base on all these. But they would need to all be the same base, whatever it is. So if I had, log base 6 and log base 7, it doesn't work anymore. All right, and lastly, we're going to use properties 1 and 2 in tandem to bring them together. So we're going to say things that are added are going to go on the top, and things that are on the bottom are subtracted are going to go on the bottom, but they're no longer added and subtracted. Now they're multiplied and divided. And so there's the result when we write using a single logarithm. Yuck, I know. The other way that we will sometimes see these questions interpreted is that your teacher will do something like this. They'll say, okay, I'm going to give you the base of some particular logarithm. In fact, I'm going to use a real one. I'm going to use natural log. So I'm going to say that ln of 2 is approximately 0.7. ln of 3 is approximately 1.1. And ln of 5 is approximately 1.6. Now, I'm going to ask you without a calculator to tell me what ln of 6 is. And you're going to look at me and you're going to be like, 1.7, 1.8, I don't know. Go from 3 to 5, it went up by 0.5. So it's like a quarter each. I'm going to guess it goes up by like a quarter. So let's say 1.85. That's a good guess. It's reasonable, but there's an easier way to figure this out. Namely, we're going to recognize that 6 is 2 times 3. And now, if we use log property number 1, we can write this as ln2 plus ln3. And we know what those are. We were told to begin with that this is 0.7 and this is 1.1. So sure enough, the answer is 1.8. So with that in mind, I want you to think about for a second, what is ln 15? Same exact idea. What is 15 in terms of its factors? 3 times 5. So we're going to write this as ln3 plus ln5, which in turn is 1.1 plus 1.6, which is 2.7. All right, what if I asked you for ln of 5/3? This is actually very similar to the last question, kind of, sort of, except it's not 5 times 3, it's 5 divided by 3. So that looks an awful lot like this, doesn't it? Log property number 2. So let's write it as such. Let's say ln5 minus ln3, which is 1.6 minus 1.1, which is 0.5. Now this shouldn't surprise us. We're doing the natural log of a number that is smaller than the base. If we did ln of e, we would get 1. Just like if we do log base 8 of 8, we get 1. And the reason for that is because 8 to the first is equal to 8. So we're doing a number that is smaller than the base. It's no great surprise that we're going to get something that is a fractional number. It's a decimal between 0 and 1. All right, what about if I said ln of 0.4? All right, 0.4 we're going to have to think about for a second. How can we rewrite 0.4? Well, as a fraction, 0.4 is 2/5. So this is ln of 2 minus ln of 5, which is 0.7 minus 1.6, which is negative 0.9. Oh, this one's negative. You can't put a negative into a logarithm. Well, no, but you can get a negative out. The domain does not allow for negative numbers, but this isn't a negative number. This is the negative number, and that's part of the range. So that's okay. And that happens when we plug in something that's smaller than 1. So if you get, let's just make a quick little chart here. If you put in bigger than the base, you will get out bigger than 1. If you put in between 1 and the base, you're going to get somewhere between 0 and 1. And if you put in something that is less than 1, you're going to get out a negative. So based on that, what we've got here does make some sense. So okay, let's we haven't used the final property, so let's consider this. What if I asked for ln of 625? 625. What number is that? Well, if you've been doing enough of these practice problems and you've recognized that you've got powers that you should know, you're hopefully going to recognize this one as 5 to the 4th. So this is equal to 4 times ln of 5, which is 4 times 1.6, so that's 6.4. If I asked you for ln of 64, now 64 is 8 times 8. It's also 4 to the 3rd power, but the way that we're going to treat it today is that it is 2 to the 6th. So 6 ln 2. ln 2 is 0.7, so 6 times that is going to be 4.2. And you can make an entire table of all kinds of things that you can figure out just using your 2s, 3s, and 5s. So this is using log properties. So we're not really using them, if we're being honest. This isn't using log properties. This is just kind of throwing them out there. So let's talk about how to actually use them. So there's a couple different scenarios where we would use these. The first is, imagine you have a question that looks like this. Now, this is awkward because to solve 3 to the x, we want to do log base 3 on both sides. But then log base 3 of 7 to the doesn't really do anything for us. If we want to solve 7 to the and have an x one here, we want to do log base 7 over here. But then when we do it to the other side, we have the same problem. So the question is, what base logarithm should we use to try to solve this? And my answer to you is, it doesn't even matter. So just to emphasize how much it doesn't matter, I'm going to use natural log. You could use common log. You could use base 3 or base 7. In fact, base 3 or base 7 does make this a little tiny bit easier. But now that we've written it like this, I'm going to say, okay, let's use that power property. Let's bring our powers out front as coefficients. So this is now x times the natural log of 3 is equal to x minus 1 times the natural log of 7. Now, does that help us? Well, yeah, actually it does, because what is ln 3? I'm not entirely sure. I mean, it was on the previous slide, but I know this. It's a number. We can go to our calculator and we can say, what is this number? And we can find out that now we have 1.099x is equal to, and ln 7 is 1.946. Again, I'm obviously getting that from the calculator. And now we have this expression. And although it's got some decimals in it, and so it's kind of gross, you don't want to really truly do it by hand, this is just an Algebra 1 question. This is like Chapter 2 of Algebra 1, or maybe it's Chapter 3, depending on your book. But we take this, we'll subtract 1.946x from both sides, so we get negative 0.847x is equal to negative 1.946, and then we'll just divide by that. And that gives me x is equal to 2.230. I hope you're following along and actually trying to do it with me. So if you've got double powers, but the bases don't match, it's not like one of those questions we did in the other video where you made the bases the same. 3 and 7, obviously, you can't make the bases the same. They're both primes and they're different numbers, so it's not going to work. So this is a case where you would need to use your log properties. You could have done this with log base 3, at which point one of these sides would just become like x instead of x times log of something, 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 right? Because if we did x times log base 3 of 3, or even we didn't have to go that far, we could have just said log base 3 of 3 to the x, and we know that this becomes x. Whereas the other side, when we did it, we would still have to use the log property. And so we would have to still say x minus 1 times log 3 of 7. But it does make it maybe a little cleaner. So you can question if we should be doing natural log or common log or whatever. I'm using natural log or common log just because it's a button on the front and I don't have to go digging around in menus to get to it, though. Because I reason I'm going to have to do some awful calculator operations anyway. So if you see a question like this, the way to solve it is going to be to take advantage of your exponent properties. Now, the other style of question that you may see is when we are solving logarithmic equations. So an example of something that might look like that. If I say log base 2 of x plus log base 2 of x plus, all right, I need to think about what number I want to use. Let's say x plus 11, right? No, I need to pick something that's a power of 2. Hold on. So I'm going to pick that number, and so we'll say x plus 12. And I'm going to make this equal to 6. And you're going to look at me, you're like, 6? It's just equal to 6? And I'm going to say, yes, yes it is. This is equal to 6. Can you tell me what number x will make this happen? And at a glance, it doesn't seem like that should be realistically possible, but it's actually not that bad. We can't just do 2 to the on both sides right now because of the way this is written. In order to cancel out a single logarithm, we can use 2 to the, but we don't have a single logarithm. Oh, but guess what we just did back here? We wrote using a single log. So guess what we're going to do right now? We're going to write this using those same concepts. We're going to smush these logs together. So we have x times x plus 12 equals 6. Okay, now we have a single log, so now we can do 2 to the on both sides. So we're going to do 2 to the 6th is equal to 2 to the log base 2 of, and while I'm at it, I'm going to simplify the inside, x squared plus 12x. And so now our 2 to the and our log base 2 cancel, and we have x squared plus 12x is equal to 2 to the 6th power, which is 64. All right, this is a quadratic. We know how to solve quadratics. We're not going to factor x times x plus 12. That just gets us back where we came from, but we are going to set everything equal to 0. And then we're going to factor if we can and use the quadratic formula if we can't. So let's see, factors of 64. We got 1 times 64, we got 2 times 32, we got 4 times 16, and we've got 8 times 8. We know that we've got a negative here, so 1 has to be positive and 1 has to be negative, and when we combine them, we get plus 12. So the bigger one has to be positive, the smaller one has to be negative, and right here, this will give us our plus 12. So x minus 4 times x plus 16 is equal to 0. So it would appear that x is either equal to 4 or negative 16. So that's the answer, right? 4 or negative 16? Not yet. There is a slight problem. What happens if we try to plug in negative 16 to the original equation? Log base 2 of negative 16, what is that equal to? What is the log of a negative number? Error, does not exist, cannot do. You broke the calculator, syntax error, domain restriction issues. Oh my God, world is exploding, universe is ending. We can't do this. Okay, you can't put a negative into a logarithm. This is what's known as an extraneous root. So when you solve a question like this, you have to test the answers afterwards. If you have an extraneous solution, you got to toss it out. So in fact, the answer to this question is just x equals 4. If you test 4, it's fine. Because if you put a 4 here, and you put 4 here to get 16, log base 2 of 4, 2 to the second is 4, so this right here is equal to 2. And 2 to the fourth is equal to 16, so this right here is equal to 4, and sure enough, 2 plus 4 is 6. All right, so there are your examples of when we use log properties. Now, the last thing that I want to throw out is some applications. I mentioned at the beginning that I want to save compound interest for its own separate video because it is so important. It is the single most important use for high school level mathematics that you will experience. Is possibly the single most important lesson you will have in all of high school. And I'm not exaggerating, I'm not clickbaiting when I say that. I legitimately believe that. But because we're going to save that, we're going to use a different example. Now, exponential applications generally fall under 3 main categories. There is the aforementioned compound interest. There is population growth, and there is radioactive decay. Obviously, this can use a decay function, not a growth function. Or anything else that grows based on how much of it there already is. So compound interest is a situation where you have more money in your account, you get more money back. Population growth, more deer in the forest equals more deer babies. More bacteria equals more bacteria being birthed. And radioactive decay, it falls apart on like a percentage basis. So these are all things that change based on how much there is. There are also a couple logarithm applications. You're going to see these far less frequently, and I'm not going to address them here. But there are a few scales of numbers that we use where we talk about them in terms of a logarithm. The first is pH, acidity. That's a chemistry thing, obviously. When you get to chemistry, you'll learn about how many like hydrogen molecules there are in a given substance, and that determines how acidic it is. The other thing is the Richter Scale, which is the scale we measure for earthquakes. The idea is that earthquakes go from very, very tiny and inconsequential to shaking the world very rapidly on the Richter scale. If you go from like a 3 to a 7 on the Richter scale, the effect is tremendous. But the reason for that is because it doesn't make sense to compare an earthquake that, let's say it had a power of 800,000. I don't know what the units are on this. And you got another one that's 900,000. Well, percentage-wise, that's actually not that big of a difference. But if you got one of these versus one that has 8, well, now there's a tremendous difference. And so maybe there's another one that's got a power level of 8 billion. And you go, oh, well, that's huge. Well, you start to lose track of things when there's so many zeros. So at that point, you really just want to go, how many zeros are there in it? And that's what the Richter scale does. It does everything based on log 10. And so does the pH scale, actually. They both are based on log base 10 common log, because they're really just saying, how many digits is it? So when you deal with either of those questions, that's what's going on. But we are going to make up a question instead that is going to concern population growth. So I'm going to ask you the question as such. A bacteria population triples every 8 hours. If it initially has a population of 50, when will the population exceed 6,000? And you might think, oh, well, 50 to 6,000, that's going to take a while, right? Well, not if it's tripling every 8 hours. Bacteria grow really, really quickly. And the reason we're picking bacteria specifically for this is because generally bacteria grow without a bound. If you talk about deer in the forest, they don't grow exponentially. They actually grow based on something called a logistic curve, where eventually there starts to become not enough food and not enough space for them, and the death rate starts to match the birth rate. So this is what you get when you have things that are not bacteria for population, if you let it go long enough. Now, for short-term basis, this part kind of looks exponential. So if you get a question that's about a town population growing, it's probably still going to be an exponential equation. Nobody's going to be like, oh, turn it into a logistic. And I'm not going to teach logistic here, but that could be a thing. We're going to deal with this as just a exponential function, though. And so we're going to say, all right, well, the amount that we have over time is going to be 50, our initial amount, times, and then it's going to triple every so often. And I'm going to say 3 to the n. And I'm going to go, n is the number of times it triples. All right. Well, we want to know when this is over 6,000. So I'm going to write 6,000 is greater than 50 times 3 to the n. I'm going to divide by 50, and that's going to give me 12. I think that's 12, right? 12. 12 is greater than 3 to the n. Hold on, am I dropping a 0? Yeah, I'm dropping a 0. It's 120. Okay. But now, well, it's an inequality. Well, you're still going to treat it like an equation. You're just going to do log to both sides. So log base 3 of 120 is greater than log base 3 of 3 to the n. So the right side of that is going to be 4.36 is greater than n. So basically the cutoff point is going to happen at 4.36. But that's not hours. That's how many times it triples, and it triples every 8 hours. So the hours is this number times 8. So I say times 8, and I get 34.86 hours. And if we had to say what hour number does that happen, we would probably round up and say 35 hours. Now, this is not the only way to write this equation. There are 2 other ways I could have written this. I could have said A of t, which I'm just going to write as A, is equal to A sub 0. A sub 0 means initial amount. When you say sub 0 in physics, it means the starting value for that. Times 3 to the, and then we could have said t over 8. And this is another way of doing it, and if you look at how it would play out, it actually ends up being exactly the same thing. Because you'll go to here, and then you'll go through these steps, and you'll get 4.36 is equal to t over 8, and then you'll end up right back here. There is, however, a second way we can do this. And I'm going to illustrate this second way because it's a more universal approach and because I like it better. So I'm going to say that time versus amount. At time 0, we have 50. And it's tripling every 8 hours. So at time 8, we'll have 150, right? And we want to know when are we going to have 6,000. So I'm just going to put t here because we don't know what that number is. Now, instead of using base 3, you can in fact use a formula that looks like this. We'll call it KECT for short. In fact, this is the compound interest formula that you're going to see where we're going to call it PERT in that other video. But this works for anything that's growing exponentially. And so rather than trying to figure out what the base is and going through all this, you could just use the KECT formula. But KECT, the C, this is A0. So I'll prove it to you. Let's test our values. Let's plug in the data point that we know. So the data point we know to start off with is that 50 for an output is equal to C times e to the k times 0. Well, k times 0 is 0. E to the 0 is 1. This just says 50 equals C. Okay, so we have now proven that C is in fact the starting amount. Now, let's plug in data point number 2. Let's say that 150 is equal to C e to the k times, and the amount of time that's gone by is 8. All right, so I'm going to divide this by 50. I'm going to get 3 equals e to the 8k? Well, we've got e to the. In order to solve e to the, we need to do ln. So 8k is equal to ln of 3. We're just doing natural log on both sides, log base e. So ln of 3 is about 1.099 for like the third time. And we conclude then that 1.099 is equal to 8k. And we'll divide that by 8, and we will get that k is about 0.137. This is the number that we need to put here in order to scale things at the correct rate. In order to triple every 8 hours, we need this number to be 0.137. Now, I'm going to do something special. Before I hit anything else on my calculator, I'm using a TI-83 again. I'm going to hit the button that says STO arrow. It's in the bottom left next to the on button. And then I'm going to do alpha A. A is, of course, right at the top over the math menu. You don't use specifically A. You can use whatever letter you want. In fact, let's not use A. Let's use K, just to emphasize that this is what we're calling it. So you do alpha K and then hit enter. And what you have just done is you have put this number into the calculator as K. And if you type K and hit enter, it's going to say 0.137. You say 10K, it's going to say 1.37. If you say K plus 2, it's going to say 2.137. Until you give it a new value for K. Now you can use X. However, because the calculator sometimes uses X for itself, I actually would recommend not using X for that purpose. But okay, so now how do we actually solve the question? Well, we do similar to what we did before. We say 6,000 is equal to, and we know now that C is 50, and we know that K is this number 0.137 times T. So we'll divide by 50. And then we'll do ln on both sides. ln of 120 is about 4.787 equals this number K. And then to prevent rounding errors, rather than dividing by 0.137, you could divide it by your K value. I did take my own advice, so I don't have it written down, but I have, just by dividing by 1.37, we have 34.95. And the reason it's different is because, as I said, I didn't actually store K. I just typed in 0.137. So there is, in fact, as you can see, some rounding error, but it's the same result. So these are two different ways to do the same question. The reason I brought up the pink way, even though the brown way seems like it's going to be more natural, is because the pink way is, I think, a more universal case, which is going to tie nicely into our last example. So I'm going to say that a radioactive isotope, which decays with a half-life of 5,500 years, which I think is about what carbon-14 is, has a current amount of 13.0 grams. Scientists studying this fossil that has the carbon-14 in it believe that the original amount when the creature died was about 200 grams. How long ago did it live? You go on, wait, what? Huh? All right, first of all, we have to define something. A half-life. Half-life is the amount of time it takes for a substance to decay to half of what it is. You see, radioactive isotopes follow a decay model where whatever amount there is, it's going to gradually taper off. And it's never going to technically hit zero, but it's going to approach zero after you get long enough out here. So our question is, if we started with 200, when do we hit the point where it's 13? And if it's cutting in half, so if this is like the halfway point right here, that's 5,500 years into the past. So how do we approach this? Well, there is a half-life formula that some teachers will bring up. And so they will say that the amount of time, and they will do something where it's 1/2 to the power. But I'm going to stay true to my word, and I'm going to use the method that we used over here with the table. And I'm going to use the Keck formula instead. So even though you may see this with 1/2, you don't have to use the 1/2 something something. It's not required. So let's consider our table of values. What do we know? We know that at time 0, we have 13 grams. And we know that it cuts in half every 5,500 years. Okay, so let's think about this. If we let another 5,500 years go by, we'll all be dead. But if we somehow were able to hop in a time machine, or if a cure for aging was discovered and we now can live forever, and we survive for another 5,500 years, and we measure this fossil, how much will there be? Well, it will cut in half at that point, so it will be 6.5. Alternatively, you could say 5,500 years ago in the past, there was twice as much, there was 26. You can use either of these. I'm going to use the first one, so I'm going to cross this out just so we don't get confused. But either one of those as a data point is perfectly acceptable. You do need 2 data points for this, for Keck. And then finally, we need to know, all right, when is the amount 200? Okay, so A equals C e to the kt. And yes, these problems do have 3 steps to them. The first is we have to recognize that C is the initial amount, so that's 13.0. And we know that because it's right here with data point number 1. Then we're going to use data point number 2 to figure out what the K is. So we're going to say that 6.5 is equal to 13.0 times e to the 5,500k. Now, I do very much strongly recommend when you solve for this, you do use that store thing, because you're going to get a really tiny number. But unsurprisingly, because we picked the numbers to make it that way, this is equal to 1/2. 1/2 is equal to 5,500k. So 5,500k is equal to ln of 0.5. So we'll go to ln 0.5 on our calculator, and we'll divide it by 5,500, and we will get that k is equal to, and it gives it to me in scientific notation. It says negative 1.26 times 10 to the negative 4th. So negative 0.00126. All right, we don't want to remember that. I'm going to hit store. That's going to bring up the little ANS arrow, and then I'm going to hit alpha k, and I'm going to hit enter, and now it is stored in my calculator. So now if anytime I type k, I'm going to get this number right here. All right. Then we're going to finish this off by finding what we really wanted, which is the value of t. So we know that 200 is equal to 13 times e to the k, which is the number we have, times t. T is the variable, k, we know what it is now. So 200 divided by 13 is 15.385 is equal to e to the negative 0.000126t. And then we'll do ln on both sides to bring that down from the exponent. And so we get 2.733 is equal to that stuff without the e to the. And then I'm going to divide by alpha k. And I get t is equal to negative 21,688.8. The answer is negative. Should it be negative? Let's think about that. We're talking about time, and time generally goes in a forward direction, right? The future is after now. The past was behind us. So if we have a negative time value, doesn't that just mean it's in the past? This is 21,688 years ago. So yes, it makes total sense. This should be negative. So it lived about 21,700 years ago. We'll just round at that point because we don't have an exact amount we're saying roughly 200. Technically, this is only one significant figure if we're saying 200. So I'm actually being overkill with that. If I said 200 decimal point, now I have 3 sig figs, and that's correct. Yeah, I know. You're suffering horrible, painful memories hearing about sig figs in math class. I won't do it again, I promise. But these are some examples, and this is all the stuff that goes on in this exponential chapter that you might potentially see other than compound interest. So again, stay tuned for the compound interest video. I find it super important to talk about it separately because it has a lot to discuss about its implications on life. But for everything else, we have hopefully finished our discussion about everything that you need to see with a couple quick examples in exponents. Thank you.